this to you guys.
All right.
Glad
Hey.
you could come, Doctor.
Lights, please.
We've been intercepting radio transmissions from Moscow. Computer can't detect.
Okay, so listen. Stop. Karen. Guys, what I talked about with this movie, A Beautiful Mind, this is about a guy named John Nash who was a professor at Princeton. He's truly brilliant. He won Nobel Prizes and so on and so forth. And what I tried to impress upon you was with this whole idea of combining like terms, that like the n squareds kind of come out and they light up a little. This is a scene from the movie, and he kind of does a little of this, so I think it illustrates the point pretty well. Yeah?
Is he a real person?
Yes, absolutely.
But he really does this in real life?
He did this back, this is, he was...
Was he dead?
No, if you notice, this is during like World War II, just after World War II, and he was, I don't know the exact years, but I want to say from, say, about 1938 or 39 through about 1990 or so, where he did all of this work. But as I said, he does have some mental issues, and that's kind of what the movie is about, this beautiful mind in so many different ways. So it stars Russell Crowe and Jennifer Connelly, who are just, you know, fantastic actors and actresses. Yeah, it's a very good movie. It won the Academy Award as the best movie of the year. So if you ever have like a rainy Saturday and you're looking for nothing to do and you want to watch a movie, this is a good movie to watch. All right, here we go.
It's a pattern, but I'm sure it's code.
Why is that, John?
Ever just know something, Dr. Nash?
Constantly.
We've developed several ciphers. If you'd like to review our preliminary data. Doctor.
Okay, so what I wanted you to be able to see with that is how, with all the data that's in front of him and all the things he sees, he's pulling out what you would call the relevant parts, and he's looking for connections within those relevant parts. So if we take that just a step further and we look at the do it question that we're doing for today, we want to do the same exact idea. We want to combine a couple of other different things, but we want our mind to try to work much the way John Nash's mind worked in that movie, where we highlight things and we pull things apart. So the first thing I notice here that's very important is that subtraction before the parentheses. What is that telling you to do? You negate everything in that parenthesis. So before I can begin, I have to do that. So that's 2n squared minus 5n plus n squared. Now, in the parentheses, what is this 3n? Everybody, what is it? So it becomes negative. Now, what kind of 4 is this? Negative. So it becomes positive. Now, this is the moment where, obviously it's a lot simpler than what John Nash was looking at in the movie, but this is the moment where the 2n squared should kind of glow and pop off the board at you, and the 1n squared. Altogether, what is it that we have? Guys? 3 what? 3n squareds. So they should glow, they should pop off, you should be able to say, okay, there's my connection. What he's trying to do in that video, he's trying to look for patterns, look for connections. And what you're trying to do is the same exact, oh, hold it.
This is the wrong one. Yeah, I was just going to
Is this the wrong one? Oh, this is yesterday's. Hold it.
You just did the wrong number.
Yes,
28.
Yesterday's.
It is yesterday's, lesson 27.
Yeah, but 28.
Yeah, but that's not the same as
Oh, it's
yesterday's.
different, yeah.
So let me go to
No, it doesn't.
window
It's easier.
28. Okay,
Same question.
here we go. Now I see why there was such confused looks about your faces. That gives me an
Well,
opportunity.
that's not the reason, but
Okay.
continue.
That gives me an opportunity to just go through it again.
What did he say? This is
Yeah,
yesterday.
yesterday's.
No, this is today's.
No, this is yesterday's. It went and it switched on me again. So. There we go. Okay, so. Again, we asked and Leanne answered before that this negative applies to everything in the parentheses. So I rewrite the beginning part. There's nothing that applies to it. But now this 3n squared was positive, it becomes negative. The 4n was negative, it becomes positive. And the 1 was positive, it becomes negative. So now the pieces of the board, if you will, kind of pop out at you. And you need to draw connections between them. So if I have 2n squareds and negative 3n squareds, what do I have altogether?
Negative 1 and square.
Right. Now I have negative 5n's. Let's see, almost see it pop out there. And then a positive 4n. What is that?
Negative 1.
Negative n. And then positive 3 and negative 1. Positive 2. Good. So there is my answer. Now that answer is what we call a polynomial. Polynomial meaning it has many parts. Like you remember learning about monotheism and polytheism? Right? 6th grade? Monotheism, the first monotheistic people were the Jewish people. Right? Oh, absolutely. Abraham got called. He one God, monotheism,
Oh, yeah,
one
yeah,
theism God. Abraham gets called, and it's from there Christianity and kind of off on the side there a little bit Islam, and they all kind of are monotheistic religions. And then you have polytheism, which would be like Hinduism, Buddhism, any religion in which there's multiple gods, the Romans, the Greeks, and so on and so forth. Poly meaning many. So when I say to you polynomial, nomial is the thing about the n squareds and the n's and the 3's and so on. Poly meaning many. This one happens to be called a trinomial. Why try, everybody? Because there's 3 parts. How many parts do you think a binomial has?
2.
2. All right. And I won't go into why we know bi means 2. Okay, now, solve for x. Distribute. 8x plus 12 minus 2x plus 2 equals 38. So all I did was to distribute so far. Be careful, a little danger there. It's not a 2, it's a negative 2. So you have to not only double, but you need to switch every sign. In the previous problem, there was a negative in front. It meant switch every sign. You have to negate everything. In this one, you have to double and negate. Now, just like before with the John Nash problem, again, see the connections here. I have 8 x's and negative 2 x's, all on the same side. How many x's do I have altogether? I have 6 x's. Then I have a positive 12 and a positive 2. What's that altogether?
14.
Very good. That's almost with a little Nash-like accent there. Good. So 6x plus 14 is equal to 38. Minus 14. 6x is 24. Dividing by 6. X is 4. Okay? Yeah, you know, I noticed a pattern on a number of kids. Like, they're copying stuff down as I go along. This shouldn't be. This stuff should be done well ahead of time. Next, describe the steps necessary to complete the second problem. Okay, so what was the first thing I did?
Negated everything.
I distributed. I only negated on the second one, right? So I distributed. Then after I distributed, what did I do? Then I combined like terms. Right? I got my 8 x's and negative 2 x's together, my 12 and my 2. Then I did not the addition property of equality, but the subtraction property of equality. Then I did the, what properties here? Division property of equality, and got my answer. Okay, good. Any question about that? No? Good. All right, so now I do want to look at yesterday's work for a couple of minutes because I want to go to some of the homework sections of it. Okay. Yesterday we talked about the laws of exponents and we went over what types they would be. And I want to go to the homework questions that dealt with the laws of exponents. Here we go. Okay. So I want to go over these 6 questions, and you can be pretty confident that you will have questions about the laws of exponents on every single homework that you have from now until the day you take the Regents, and possibly even after that, okay? Now, in each of these problems, there is an easy one and there is a more challenging one. First one. First, let's review the rules very quickly, even before we go on. Oh, Olivia, you're going to get me on it now. X to the A times X to the B is what, everybody? Oh, Michelle's cranking out the yawns. Go ahead. Look what you did. Oh, you're going to yawn too? Oh, okay. What is it?
X to the B.
No.
X plus.
Wait, is that a B at the top?
Uh-huh.
Oh, what is it equal to?
Yeah.
Oh, X equals A plus B.
Yeah, very good. Okay, next one.
What doesn't matter?
X to the A over X to the B. What's that going to equal?
X
To the
equals
A
A minus B.
Why?
Yeah, Wyatt, she was answering.
No, she wasn't.
Yes, she was.
You're doing it pretty slow.
That's okay. Not everybody exists on Wyatt's speed. Okay, next. X to the A to the B is equal to X to the AB. Okay, so now here's the deal. Yeah, you felt you had to speed up on that one, didn't you? All right. So what I want you to notice here is that there is a pattern going on. It might not be obvious, but there is most definitely a pattern. Here we're multiplying the bases and we step down to addition. Remember, multiplication is just repeated addition. It's if you will, addition on steroids. It's the next step up from addition. This is division, and it steps down to subtraction. Division is like subtraction on steroids, okay? And then here we have exponentiation, which it steps down to multiplication. So the simpler form of multiplying is addition, the simpler form of division is subtraction, and the simpler form of exponentiation is multiplication, and that's what each of these things steps down to. So just remembering the idea of step down and what the similar operation is, that's the easier form of it, multiplication to addition, division to subtraction, exponents to multiplication, you can remember what the rules are. Andre, did you have a question?
What if there's addition between the two x's?
Then you can't do it. It has nothing to do with the laws of exponents. There is no law of exponents for this. This is an x to the a, this is an x to the b, I can't combine those. In order to put things together, they have to be the same type. Now, if it said x to the a plus x to the a, well, that's one of those things plus another one of those things. Well, altogether, that's two x to the a's. You can't do it. It's got to be the same exact type of thing in order to add. On the face of the earth, you can only add the same kind of things. I can add calculators to calculators. I can add notebooks to notebooks. But if I say to you, what's 3 calculators and 7 notebooks, what are you going to tell me?
3 calculators and 7 notebooks.
That's it. If I say I got 2x, if I say I have an x to the a and I have another x to the a, you're going to tell me you have 2x to the a's. If I say I have an x to the a and an x to the b, that's what you have. You have an x to the a and an x to the b. Yeah, that's it. Okay, so
What if you say 10?
anyway, we're going to go to 16a here. This is the easy form. X to the third times x to the eighth is what, everybody? X to the what?
11.
11, good. Now I come over here, and I'm going to multiply coefficients. Now, we defined for you yesterday coefficient. What's coefficient mean again?
The number in front.
Number in front, good. So what's negative 4 times negative 7?
28.
28. Now I'm going to add exponents. A to the
Eighth.
8th, B to the
Eighth.
C to the
4.
4. Sometimes kids put 3 here, but you need to remember there's really a little 1 here, and we don't always bother to write it, so don't forget about that, okay? All right, next up, x to the 5 over x to the 4 equals?
X to the 1.
Good. And then over here, dividing coefficients, I get
2 and 1.
2, and if you want to write to the first, you could. It's not wrong to, but it's not necessary to. Next one, n to the 5th to the 4th is?
N to the 20th.
N to the 20, good. This is the tricky one. Danger, danger, danger here. So many kids write 3v to the 9th, and that's wrong.
Oh. 9
No, that's what other kids write. That's also wrong.
20B. I mean 21.
21.
27 B to the 9th.
27v to the 9th.
I like
Redemption!
This, look, it's the easy part that all kids get is the v to the third to the third. So when you raise a power to a power, you multiply to get 9. But you have to do 3 to the third, which means 3 times 3 times 3 again. So that's 27. Mia,
Remember, letter E is different on our paper.
are you looking at yesterday's sheet? We want you looking at yesterday's sheet. I want you looking at 27 right now. Sheet 27.
There's 2N.
Yes, 2 and
Wait, I don't even see it.
Yeah, it's 2N.
So I think.
It's just, there's no 2N. See, that's what we're.
Oh yeah, mine says 2N. 5 to the 4.
Okay, so over here it had a 2?
Yeah.
Yeah, so that would then be 16n to the 20th. Okay? Same idea.
I still got it.
All right, any questions?
No.
All right. So, that checks off last night's homework. Let me shrink that down. And let's talk now about lesson 28, which we did 1, 2, and 3. So now we're ready to go forward with the lesson for the day.
28.
Okay. Everybody do, on your paper, 48 times 24.
48 times 24.
Yep. Okay, 48 times 24. Now, you know, it's funny. You have your way of doing it. Do you ever, like, show your homework to, like, your grandparents? And show them how you subtract and stuff, and they look at you and they go, what are you doing?
Yeah, I've done it.
Right? They go, I don't even understand how you're
It's
doing it.
funny.
The truth is that they used to do things very differently, and in fact, many parts of the world do things very differently than we do. They're trying to change it even more with the whole Common Core thing, right? You have your little brothers and sisters come home and go, what the heck is this? And you look at their homework and you're like, how do you, this is insane. What are you coming up from? Well, I'm going to show you how most of the world does 48 times 24.
What is that?
Are you good at making?
Oh, I've done this before.
I've done
I've
it before.
What?
never done this before.
8,
No, like,
I hate
16,
I love
16,
this. It's so easy.
32, and on the diagonal,
I
2,
don't know.
12, 15, 11, 1. It's 1, 1, 5, 2.
What the heck?
I've done this before. You got the wrong answer.
How are you using boxes?
Well, that's the question. How are you using boxes? The boxes actually work pretty well. To figure out what goes here, I just did 2 times 4 is 8, and I wrote it 0, 8. This is 2 times 8 is 16, 1, 6. This
That's
is
wrong.
4 times 4,
No,
16,
no,
1, 6. And this is 4 times 8, 32, 3, 2. And then I add on a diagonal. See, the way you do it,
It's easy.
well, this is easier, believe it or not. It takes longer, but it's easier. The way you do it is as follows. And by the way, if you have sloppy handwriting, not minor, this is very possible. You will get this wrong much more. The nice thing about this is everything has a little place to go in its box. And you can't screw up it, and you can't make it too ugly. This, sometimes, you ever do like a really big one, and sometimes the lines kind of you're not sure which one the number's in, and you wind up getting it wrong? All right, so what you do is this. You go straight up and down. You go 2, 3, 16, 19, and then 16 and 9, then you go 2, 5, 1, 11, 11, 52. So if you notice, you are multiplying on diagonals and adding straight. This is multiplying straight and adding on diagonals. But you come up with the same answer either way. Now, I could also do that to 125 times 314. In fact, the bigger I make it, the easier the box is. So, I don't want you to actually do this right now, but you could do, if you wanted to.
How do you know how many boxes?
It's 3 by 3. 1, 2, 5,
Wait, can we
3,
try
1,
this?
4. You could do it at home later. But you could then fill in each box. This would be like 0, 3, 0, 6, 1, 5. And you could do them all and you could put it together. Now, the reason I bring this up is to let you know that there is this whole other way to multiply that the rest of the world pretty much does. In fact, I was first taught that when I was around 20 years old. And the way it was taught to me, it was called Russian multiplication. Because if you were a student in Russia, which is clearly a country that is, modern, you would be learning how to do it that way. I was also told that's how Abraham Lincoln learned how to do. Oh, there you go. I was told Abraham Lincoln learned how to multiply that way. I'm sure George Washington did. Yes.
How do you do it that way?
You fill in the boxes and add on a diagonal. We're going to do something very similar here. We're going to do something very similar here. It's not, excuse me, it is not my intent to spend the period going over how to do arithmetic with just numbers. But that idea of a box applies to what we're about to do right now. So I'm actually going to show you two ways to do this. I'm going to show you what I call the box method, and then as time goes on, we're going to change the box to what we call double, or in the third case, triple distribute. I hope I get through all of them today. If not, we're going to again do the same sort of thing on Monday. So you'll get a second shot at it, and if we don't get past the box method completely into double or triple distribute, we'll finish it up on Monday. So, let's start with this one. And this I'm going to go much slower, and you're going to do it with me. First off, I don't need diagonals because you can't get like 0, 8 here. So what I want you to write, and I don't care where you write it, you can put x minus 5 on one and x minus 4 on the other. You can reverse which one goes where. It makes absolutely no difference, which is another really cool thing. The reason it doesn't make a difference is because multiplication is commutative, and by switching the order, you're just using the commutative property, so it makes absolutely no difference. And I have found that many kids like this. In fact, there's a young lady who used to go to school here. I adore her. I think she's great. Alexa McCarthy. I don't know if anybody knows Alexa, but she's sick from the high school. She's on home teaching for a couple of weeks, and I'm actually helping her, and she's doing 11th grade Algebra 2 stuff, and she still uses the box method to do some of the Algebra 2 stuff. And I'm like, well, didn't you move on past that to double distribute? She goes, no, I like the box method. I'm very happy with the box method. I just want to keep doing the box method. So this is what the box method does. To get this box, this is like Punnett squares. Do you remember Punnett squares?
No,
Science, genetics,
no. Why don't I try again?
dominant gene, recessive gene, all that
Oh,
kind of stuff.
yeah.
All right, to get this box, I'm just going to pair these two up. What is x times x?
X.
X times x is x?
X.
X
1,
squared.
2.
What's x times negative 5?
X times negative 5.
Is negative 5x. What's negative 4 times x? Negative 4x. And what's negative 4 times negative 5? Positive 20. And the only thing is now, we are going to make what I call, after one of my former students,
The jelly bean.
the Fuji peanut. Okay?
Like a weight.
We're going to add on the diagonal because these are like terms. So I have an x squared. I have a plus 20. Those are the only ones of their type in the whole problem. But then I have a negative 5x and a negative 4x. You can do the little John Nash thing where it kind of pops out and glows. Okay? Negative 5x, negative 4x, all together, negative 9x. So I multiplied a binomial times a what? Binomial, and I created it is a polynomial, but be a little more specific. Trinomial. A binomial is also a polynomial, but this specifically is a trinomial. All right, you try the next one. Let's see if you can do it. Stop whining, Leanne. Fill in each of the boxes and then do that Fuji peanut where you can combine the ones on the diagonal. Okay. All right, so what do we got in the first box there? X times 3x. What does that give me?
3x.
No, it doesn't give me 3x. 3x squared. What's x times x, everybody?
X squared.
So 1 times 3 is 3. That's the coefficients. X times x is x squared. Next up, negative 7 times 3x. What do I get? Negative 21x. And this is an important point. You have to be careful about putting the signs in there, positive or negative. Some kids just leave the signs out. That's a mistake. Positive 4 times x. Positive 4x. Negative 7 times positive 4.
Negative 28.
Good. Now, adding on the diagonal, here's my Fuji peanut. I get 3x squared minus 17x minus 28. Okay? 3x squared minus 17x minus 28. Does that make sense? How many people got that right? Okay, about a third of the class. All right. So now, we take a look at the next one. And this time, it's not a binomial times a binomial. What is it this time? Trinomial. Now, you can still set up the box, okay? It's just gonna be a little bit bigger box. I'm gonna set up a 3 by a 2. And then this will be x plus 4, and this will be x squared plus 5x minus 2. Go ahead, do it. Okay, so what is x times x squared?
X cubed.
X cubed. What is x times 5x?
X, 5x squared.
5x squared. And make sure you put the positive there. If you don't put the signs in, you're going to make mistakes. What's x times negative 2?
Negative 2x.
Negative 2x. What's 4 times x squared? Plus 4x squared. What's positive 4 times positive 5x?
Positive 20x.
Good. And what's positive 4 times negative 2?
Negative 8.
Negative 8. Now you're going to add on the diagonals. There's a negative 8. Combine these two here, future peanut. 20x and negative 2x is what?
18x.
18x. Future peanut. 5x squared and 4x squared.
9x squared.
And that's a positive 18x. Positive 9x squared. And then there's my x cubed to start. So that's the answer. X cubed plus 9x squared plus 48x.
48.
Pardon me, minus 18x. Or plus 18x. I had a hard time reading the symbol there. Minus 8. Now, the last thing I want to discuss is, what shape is this?
A rectangle.
It's a rectangle. So you can also look at this as the area of the rectangle is x cubed plus 9x squared plus 18x minus 8. Doing this multiplication, isn't it true that to find perimeter you add sides, but to find area you multiply to find sides, or to find area? So I'm literally, the area of this little square in the upper left is x cubed. The area of this one's 5x squared. The area of this one's negative 2x. By combining each of these 6 areas on the inside into one expression, I have written an expression for the area of the rectangle. Yes?
Does it matter what part of the rectangle you put each equation on?
Well, in this case, because it's a 3 by 2, you want the side that has 3 columns to be on the side of the trinomial.
Could you like flip it the other way?
Oh yeah, you could make it, if you will, the width go up here and the length go down this way, sure. And you'll always see this diagonal effect with the future peanut. All right, it'll always be there. Now, I noticed that at this point in time, I don't go into the double distribute. We will talk about that on Monday. But this is a solid technique for being able to get this down pat. All right, any questions?
No.
All right, do a great job on your homework. New series of quizzes next week. Test on Halloween. Lots of this is all algebra. Lots and lots of algebra on your next test. Okay?